big idea, this is exciting, we're starting it today. The second big idea of calculus involves concepts and techniques of integration. The branch of calculus that may be used to find area. Recall, the derivative of distance is velocity. The derivative of velocity is acceleration. Okay, example 1, distance traveled. Consider an object moving at a constant rate of 3 meters per second. Well, the nice thing about, so they're inverses of each other. So it's like saying 3 times 2 is 6. I can check my answer by going 6 divided by 2 is 3. So same thing with integration and derivatives. You'll be using derivatives to say check your answer because you're very confident at this point in derivatives. It's going the other way that you might second guess yourself. So then that's when you would find the derivative just to check, right? Okay, so how far would the object travel after 4 seconds? It's not supposed to be a hard question. If you're moving at a constant rate of 3 meters per second, how far would you travel after 4 seconds? Yeah, 3 meters per second times 4 seconds, the seconds cancel, and we get 12 meters. Does everybody see? If we were to draw a graph of velocity versus time, what would equal the area under the line after 4 seconds? So just so you know what this is the, I don't know why that's the constant line. This is the actual t-axis, just so you can see it a little bit better. This is the v-axis there. And so if I were to do a constant rate of 3 meters per second, do you see after 4 seconds, what is this area that this would be? This would be a 4 by 3, so that would be 12 meters as well. Hey, look at that. Do you think that there's a connection? Yes. The accumulation of area under a velocity curve would be the net distance covered. So what happens if the function isn't constant? So if we have a curve like this, it's a little harder to find the area, right? It's not just a nice little rectangle. So this section develops a method to find the area that lies under a curve, y equals f of x, above the x-axis and between the vertical lines x equals a and b. So essentially this shaded region, right? So does anybody think they know how I could figure out the area of that kind of crazy looking thing? Break it up into little shapes. So what shape do you want to break it down to? Rectangles, yes. Rectangles are a great way to break up a shape. So one way to approximate this area is to cover it with vertical rectangles. Find the area of each rectangle, then add the areas. Does everybody see? If I were to break this down into a rectangle here, and then another rectangle, and another rectangle, do you see I'll eventually get the area approximately? That's not what you figured?
Well, I mean, like, I understand that.
Yeah. It's easier to do it as vertical. If you do it like this, and then you'll still have to break those down, right? So then it's easier to do little rectangles like this, right? So, of course, what about the stuff I'm missing at the top? Then I could, and this is what we're going into, then I could actually do rectangles that are maybe above, you know, so then I'm overestimating, right? So then there's a happy medium between. So we're going to go over all that. So if the rectangle do a good job, if the rectangle does a good job of covering the shaded area, the sum of their areas will be a good approximation or estimation for the actual area. All right. So here is a graph of y equals x squared from 0 to 2. And we are going to divide it into 4 equal sub-intervals of using 3 different methods to find the area under the curve. So the first one we're going to do, which is called the LRAM, which stands for left-hand rectangular approximation method. So that means you're making the rectangle, whatever height is on the left side of the rectangle, that is the horizontal line that goes across. So the first thing we need to do is break this down into 4. So does everybody see, if I were to do that, there's that, right? Then we could break this into that. Then we can break it into halfway, whatever that is, and halfway. So there's my 4 subsections, yes?
Why 4?
Because the question said to do 4. Honestly, if you do more, it's going to get harder, and because you're going to be adding up way more stuff. So now because we're doing left-handed, that means wherever it hits the curve on the left hand of the rectangle, does everybody see there's rectangles in between here, right? So from 0, does everybody see, and this is kind of confusing at first to see this, but does everybody see if the curve is right here on the left hand, that you're actually, the rectangle is basically that. This rectangle is that. This rectangle is that. And this rectangle is that. Yeah? So does everybody see we have 4 rectangles from 0 to 2?
Oh, it is the...
So this one, obviously, we're not going to draw, because that would be past 2, right? So if you want, I can shade this in so you can see it a little bit better. Yes? Okay. So just so you know, the subintervals, the way you calculate it is, if you're going from 0 to 2, it's going to be, n stands for the number of subintervals. Sorry, n, the subinterval, I say widths, maybe. It is 2 minus 0 divided by n, which is 4, is how I got each length is a half. Does everybody see a half here? The width is a half. Okay, so then in order to calculate this, we're going to just do basic, I don't know, when did you learn rectangle area? Grade 4? Right? Grade 9? So the area is equal to, so what's the width here? Well, it's 1/2. What's the height there? 0. Plus, what's the width here? 1/2. What's the height there? How do I figure out that height there? It's not a height of 1.
It's what's in between 0 and 1 squared. What about that first one? Oh.
That first one. Okay, does everybody understand this curve is x squared curve? You should be able to figure out the height there. 0.25 is a quarter, right? Why is it a quarter? Because what each width is 1/2. So going from 0 to this is 1/2. If I plug it into the x squared formula, that means this height is a quarter. Yes? Okay, the next width is again 1/2. We know all the widths are 1/2. So, what's this width here? I'm sorry, what's this height here? 1. Plus 1/2, what's this height here? So this is 3/2. So if I put that into the formula, I'll get 9/4. Okay, and then I'm going to add this all up. So I get 0 plus 1/8 plus 1/2 plus 9/8 1/8 and 9/8 is 10/8 and a half is 4/8, so that'd be 14/8, which is 7/4. Yes? Okay, so in this curve, because it's concave up, the left part of this, would this be an overestimation or an underestimation of the area under the curve?
Under.
Yes. Underestimation. Well, you'll see, right, if you're going from the left, that'll be under. By the way, there's a much faster way. Does everybody see the width is a half for all of them? So if you would have just went 1/2 times the sum of the heights, so 0 plus 1/4 plus 1 plus 1 plus 1 plus 9/4, you would have got 1/2 times 1/4 and 9/4 is 10/4, and 4/4 is 14/4, right? So then you'll get the same thing, right? 7/4. So that is a much faster way, and that's what we're going to do from now on. I just didn't want to start that way because you would have went, whoa, you know, what are you doing? So now does everyone understand? If all the subintervals, the widths are all going to be the same, it's much faster to take the width and times it by the sum of the heights. Okay, so we're going to do the same thing again, but this time we're doing right-hand method. So again, here is there, and there. Yes? 4 subintervals. This time we're doing the right-hand method, which means you look to the right side of the interval to make the rectangle. And it's pretty obvious right now it's going to be an overestimation. Does everybody see that? Do you see I'm starting at the right-hand side this time and then creating my rectangle? That's why it's called the right-hand method. And in a second, we're going to do the midpoint method, and that's going to be halfway between the two. So anyways, so the area here, again, the width is 1/2. So now we're going to add up all the heights. What's the height of the first one? What's this height right here? Well, 1/2 is the x, but it's 1/4, right? Plus, what's this height here? 1. This is 3/2, so that would be 9/4. Plus, this would be, I know it doesn't look like that, but what is it? It's 4. Yeah. Notice something about these heights here. It just got shifted over, right? Yes? Okay, so quick and easy way, I would add up the whole numbers. I get 5. And this I get 10/4. And so 10/4 and 5, well, that's 20/4. So I get 30/4, yes? So I get 1/2 times 30/4, which is 15/4. Okay, by the way, if I go back just to compare this, this is 7/4, which is what, 2 1/4? No, 1 3/4. Yes? 15/4 is 3 3/4, 3.75. So do you see this is an underestimation, and you can see visually this is a overestimation. Just so you know, right rectangles aren't necessarily always going to be an overestimation. It depends on whether it's concave up or concave down, right? Okay, the next method I'm going to do, like below. Yes, yes, yeah. Yep. Okay, the next one we're going to do is the midpoint. So now we're dividing the 4 sections again, but instead of taking the left hand or the right hand, we're finding the middle. So again, There's my sections off. Okay. But this time, it's going to be halfway, wherever it meets it halfway. I might use a different color pen here just so you can see that. So halfway between 1.5 is 1/4. So wherever that hits it, there's I'm making my rectangle. Do you see? There's my first rectangle. Here's the halfway, so there is my next rectangle. There's my halfway, so there is my rectangle. Yes? Halfway, say, is there, so there is my rectangle. It's not the perfectly drawn one, but does everybody see? Kind of a better estimation, right? It underestimates here and overestimates there, so then it should kind of work out pretty good. Yes? So again, the subintervals, we're doing halfway between wherever that height is, we're drawing the rectangle. Halfway between wherever that height is, we're drawing the rectangle. The height. So this is going to be 1/2 times, what is the height of the first one? 1/16, because it's 1/4 going in, so I'm getting a 16th. Does everybody see how I'm doing that? Do you see, this is the halfway mark, or this is, I guess, the interval. Halfway would be 1/4, right? And if you put 1/4 into the curve, you get a 16th. So plus the next one, what's this height? That would be halfway between 1/2 and 1. So that's 3/4, right? So 9/16. So then we have a halfway mark between 1 and 1.5, because this is 1.5 or 3/2. So what would that be? What's halfway between 1 and 1.5? 1.25, which is 5/4, which is 25/16. Yes? And then my last rectangle is halfway between 1.5 and 2, which is 1 3/4. 1 3/4 is what? 7/4? Yes? So that would be 49/16. Yes? All right, let's add her all up. So we get 1/2 times, that's 10, 35, 35 and 49 is what? 84/16? Yeah? 35, because I just added this up. Somebody can check my math, though. So this is what? 42/16, which reduces to 21/8. And that is 2.58 is 625. And because this is units, I should be saying units squared, actually, in all these. Maybe we should go back and say units squared. Units squared. Okay, so look at that. 1.75 was an underestimation. 3.75 is an overestimation. And this is, again, an approximation. If I told you what the area is, the actual area, and you will be learning what the actual area is and how to calculate it. Does anybody know? Just by chance? It's 2.6 repeating units. So it's a pretty good approximation, the midpoint one. So the question is, how do I know if I'm over or under? They probably wouldn't ask you necessarily that, but in about 2 days, Carson, you will know if you're over or under because you'll know how to figure out the actual. Yeah. So you're thinking, oh, why are we doing left and right? So the way they ask this on the exam is they usually have a table of the values. So you don't actually see the curve. I'm just doing it as a visual for you right now. But usually they'll have it in a table, and you'll have to know whether you're taking the left of it or the right of it to plug her in. So let's try this one. Approximate the area under the curve for the square root function. I don't know why my 0 looks like it's shifted over, but anyways. from 0 to 4, we're going to pretend 0 is actually at 0, not where it actually is written there. And we're going to split it into 4 sub-intervals doing 3 different methods again. So, again, it's pretty easy to do in my head. If I'm going from 0 to 4 and I'm splitting it into 4, then each one's going to be, one. Oh my lord, that is a bad vertical. Right? Okay, so we're going to do left this time. Left means it's coming from the left. So that means this rectangle is basically I should use a different color, hey? This one is pretty much non-existent. Does everybody see that? So then if I'm coming from the left here, you can see very quickly it's going to be a underestimate again. Yes? Okay, so I'll give you a second to figure out the area. We may use a calculator for this one just to get a rough estimate. Otherwise, we're going to be leaving it all in square roots. So you can grab your calculator. So the area is 1 times 0 plus, what's the height of that one? Yeah. Plus, what's the height of that one? Square root 2 plus, because it's a function, you just plug her in, right? So then the next one would be square root of 3. So then I would just plug it into my calculator, because obviously, you know, you can't really simplify too much here. And we'll do 3 decimal places. Remember, it's just like pre-cal. You do not round until your final answer. So you get approximately 4.1462 units squared. What? So this is a overestimation, right? So I get 6.1462 units squared. I should do, oh, sorry. Okay, I'll slow down. Sorry. Okay, so anyways, we got 4, 3, 1. Okay, so halfway would be here, yes? Halfway would be here. Halfway. And then halfway would be here. So you can see visually, it's a pretty good approximation. Like you'll see that, and obviously mine's not drawn to scale per se, but this is a little bit bigger than that part. This is a little bit bigger than that part. This is about the same, and this is about the same. So anyways, so the area is still a width of 1. So now, if I put, this is halfway, it's the square root of a half, right? And this is 1.5 or 3 over 2, so it's the square root of 3 over 2. Yes? Everybody good with what I'm doing? And then 2.5 is 5 over 2, so then this would be the square root of 5 over 2. And then this is 3.5, which is 7 over 2, so this is the square root of 7 over 2. So I add her all up and I get approximately 5.384838. 838? Okay. Okay, and so just so you know, the actual area, and like I said, I'm not going to tell you how I'm getting this yet, is 5.33. It's basically 3 repeating units squared. So you can see that the midpoint again was a better approximation than the left or the right. So anyways.